Now, you you know things are always going to get more complex. So we talked about series and parallel, but there are a lot of circuits that are more complex than that. And so we're not going to dig uh, into super complex circuits, but we want to have some tools that we can use to deal with more complex circuits, and that's where we'll start with today. Okay, so a lot of circuits are going to have parallel and series relationships. So let's look at this guy. How would we start to solve this circuit? Say we knew the voltage, we wanted to know the current. We'd work through equivalent resistances. Okay, so we would take a system here, which is all uh, parallel resistances, and we would come up with RP, right? The equivalent resistance for these. And then we'd come up with the equivalent resistance for these, and we'd put those in here. This is RP calculated from this. This is RP prime calculated from this. And then we have this circuit. Okay, now what do? Well, we take these guys, they're in series, and we can calculate those in series. So we come up with the equivalent resistance series. This is equivalent to these two together. And then we have a parallel circuit here, right? So we take these two and calculate those as a parallel resistance. Okay, then we put that there. And then finally we have a series resistance here. And we calculate the resistance there. And so we come up with a equivalent resistance. This is an equivalent resistance to all of these resistors arranged in that particular fashion. So we combine all of those equivalent resistances to find an overall equivalent resistance. And we'll do some examples of that in class. I think it's not as complicated as it sounds, but it takes a little practice. We've talked about resistors in parallel. We could also talk about batteries or power sources in parallel. You've opened your toys or your electronics. Um, Sometimes you'll see batteries lined up like this, right? That's called a parallel arrangement. And sometimes like in a flashlight, you'll see them stacked on top of one another, so that um, they add to this, and that's serial. And it does different things. A parallel arrangement gives you the voltage of the battery itself. And the series arrangement sums those voltages. Okay, so if I put this in series, let's say this is a 5-volt battery, right? This is going to be 0 volts. This is going to be 5. This is all going to be approximately 5. This is the internal resistance of the battery. And then this is going to bump it up from 5 to 10. So this would be about 10 volts. This would be about 0 volts. So they're working in similar kinds of ways, right? And they have different purposes, right? If I want to um, increase my voltage, I'll put them in series. Now this has the problem of these are internal resistance. You're going to add to the internal resistance within the batteries, which is going to weaken um, your overall voltage. Batteries in parallel have the same voltage as one battery, but they can supply more charge, and they also have to deal with that internal resistance a lot less, because this is going to be parallel, so that resistance is going to be very small, so we don't have to worry about that much. So they can supply a lot of charge at a lower voltage. And finally, we need to talk a little bit about meters. Um, It might not seem like meters are that important, but they're really crucial. There are meters in all sorts of digital instruments. Any instrument on your car that's measuring your speed, measuring how much gas is in your tank, almost all of those are digital now. And so they're measured in some way by figuring out what the voltage or a current in a circuit is. And there are a couple of important things to recognize here. Um, First of all, just to give you an example, how does a digital thermometer work? Well, a digital thermometer has a resistor in here that is sensitive to temperature. And so if I heat it up, it's going to change the resistance of that resistor. So if I set a voltage across that resistor, and that resistance changes with temperature, I can then measure what the current is flowing through that circuit, and it's going to tell me what the temperature of the resistor is. And that's how a digital thermometer like that works. Voltmeters are going to be set up like this. They're always going to be in parallel to your load, right? So if I want to know what the difference between the voltage here and the voltage here is, I'm going to put it parallel to that load there. Why? Um, well, you want to know, like we said, that the series of resistors is going to be like a voltage divider. So you want to connect this wire to that wire. Do you want a big resistance there or a small resistance? Well, you don't want to affect the current, right? If this was a small resistance, what would happen to my current here? It would say, oh my God, I don't want to pass R1. Oh, here's this easier way. Whoop! And you'd basically be short-circuiting your load, and you'd destroy the purpose of your circuit. So what you do is you make a voltmeter with a really high resistance. So the electrons come along in here and they say, oh, I don't want to go that way, and they're just going to go my normal way through my load. And so that's why you want a voltmeter with a high resistance. Ammeters, that is current meters, are placed in series. And again, we can ask, do we want a high resistance or a low resistance? Well, let's say I have a 12-volt circuit here, and I put a huge resistance here. Well, like you're going to get quite a voltage drop across here, and it's going to reduce your current. So I might end up with 12 volts here and 1 volt here, and all of a sudden my circuit's not working very well. So with an ammeter, you want a really low resistance that's going to allow the current to flow through there as if that meter wasn't there at all.